So the last example from your 4.4 section, your 4.4 notes. There's an example in your textbook. I think it's example 4 in section 4.4 that you might like to read through first. This is from the problem section at the end of 4.4, sort of a variation on the problem that they did the example for on. So I want to design a can, and I want to use the minimum amount of material. The problem is, the material I'm counting, it doesn't just count the material that ends up in the can. I'm going to cut the ends, the circles for the top and the bottom, out of a square. So there's some waste, there's leftover material that I can't use for anything else. So I have to take that into account when I write my equation for how much material I use. So fortunately, this time, we happen to be given an equation for the amount of material that we're going to be using, and we can go through our 7 steps now. So I have been asked to minimize A. So A is the amount of aluminum used in the can. I'm going to minimize A. My hint that this is an optimization problem, most economical. So that's my superlative, most economical. So cheapest, right? What's the cheapest can? So I want to minimize a function A, and A has been given. But the interesting part about this problem is the function, even though it's been given, you might think that makes this problem easier. Notice that the function A, it's a function of both R and H. So the most work in this problem comes from rewriting that equation for A so that it contains only one variable. So how can you do that? What we have to notice is that we've been told at the beginning, they sort of snuck it in there, that we know the exact volume for this can. And it's going to be exactly 1,000 cubic centimeters. So let's write up what we have so far. So we're still here on step 2. We have a function A, but we have to find a way to make it contain one variable, not two. So I'm going to come to the side, and I know that the volume of a right circular cylinder is pi r squared h, and I know that the volume of this can is supposed to be 1,000. So 1,000 is equal to pi r squared h. The idea here is I'm going to take this equation and solve it for one of the variables. I think it happens to be easier to solve it for h, but you could solve it for either one. I'm going to divide both sides by pi r squared. And I now have an expression for h. I know h is equal to 1,000 over pi r squared. This I can substitute in for the h in my a function. And now I will have an equation for a that contains only the variable r. So watch this. So we know a is going to be 8r squared plus 2 pi r, and instead of h, I'm going to plug in 1,000 over pi r squared, and I'm going to simplify. So I've got a is going to equal 8r squared. The 2 multiplies the 1,000 to make 2,000. The pi's cancel. I have an r here and an r squared in the denominator, so I'm going to have r in my denominator. So now I've finally finished with step 2. I have a formula, a equals 8r squared plus 2,000 over r, and that's the function I want to minimize. So step 3, I'm going to need to find a prime. So I'm going to clear this up. So to find a prime, I need to take the derivative of 8r squared. That's going to be 16r. For me, when I think of taking the derivative of 2,000 over r, I think of that as 2,000 times r to the negative 1. So the derivative is going to be 2,000 times a negative 1 times r to the negative 2. So you could write 16r minus 2,000 r to the negative 2, or that's the same as 16r minus 2,000 over r squared. So I've written a prime here. Next step, I'm going to use that derivative, a prime, to find critical points. So I'm going to set a prime equal to 0. So what I have, I'm going to have 0 is equal to 16r minus 2,000 over r squared. The way to solve that equation without getting accidentally multiplying through by 0 or something like that is to make 1 fraction my common denominator is going to be r squared, but that first term, the 16r, doesn't have any denominator at all. So I'm going to multiply top and bottom by r squared. I'm going to get 16r cubed over r squared minus 2000 over r squared. Already has the correct denominator. And you can see I'm going to end up with, so 0 equal to 16r cubed minus 2000 all over r squared. Now this derivative, a prime, is undefined when r is equal to 0, but I'm not even considering possibilities of r equaling 0 because I would have a volume that's not equal to 1,000 cubic centimeters. So the only solution I'm going to get here is when I set 16r cubed equal to 2,000, and you're going to find that r equals 5 is going to be my one critical point. And I'll just point out here, I did make a graph. Oops. Just to prove that I graphed the a function, and just to kind of make sure that I was going to have a minimum. And you can see it does kind of look like when the input variable is 5, that's the lowest point on the graph. All right, so let's write up what we have so far. Step 4 is to find the critical points. So I have found now that r equals 5 is my one critical point. I don't have any endpoints in this scenario. I could let r be as big as I want. So what's left to do is to make my table of values. Actually, I don't know that I actually need it here, but let's just see what we've got when I have r, the volume of the can. R is 5 is the only interesting place to look that I got. Am I sure that it's a minimum? I'm sure that it's a minimum because of the graph that I just showed you. That was when the input was 5, the graph had its lowest point. So I can plug 5 in here. I end up getting 600 as the volume. But notice we have a slightly different question we've been asked. That says here, what is the ratio of H to R for the most economical can? Well, we know that R is going to have to be 5. They've asked us to find the H that goes with it, and then to just make a ratio. So what is H going to be when R is 5? Well, remember that 1,000 was equal to pi times R squared times H. We know R is going to be 5. Can divide both sides by 25 pi. I'm going to get 40 over pi equals H. So to answer their question, I'm going to make the ratio H to R. So that's 40 over pi over R is 5. So that's equal to 8 over pi. Or I think in the back of the book they even said 8 over pi to 1 means the same thing. There you go.